Okay, hello again. So today we're going to cover a topic that is very common, the Ethereum community, but I think for the Cartesi community, it has some special properties. So let's try to review a bit the traditional metering and see what are the differences that we face. So we're gonna first go through the problem of running code from untrusted sources, explaining what typically people do to secure the execution, what is new in blockchain, and why metering is this new piece that was not present in most of the techs before. And then I'm going to explain this difference between what I call adversarial and cooperative metering, which appears for Cartesi, but not for Ethereum, for example. So running code that is unpermissioned is something that is ubiquitous. So it happens if you have, for example, a computer in a university that several different students share. So you have different users that have different permissions in the file system, on the network, so on. But it also happens, for example, if you have a phone that you download apps for, or you execute JavaScript code on a browser. Here in the corner, you have an example of a game that I find very fascinating, where people build robots, code robots to play against each other. It's called scripts. Of course, in blockchain, this happens all the time, as we'll detail more soon. And in cloud infrastructure, you basically say if you're running AWS, you're running code from several different developers that you not necessarily trust. So usually the threat model is the host is executing code from several different people. Some of them, let's call them users here. They are the people you actually want to provide an execution environment for. And the attackers, they just pretend to be users, but they're trying to usually compromise the code from other users. So there is no value in your technology if you're not actually providing code execution to your users. Otherwise, you just shut down and you don't allow for untrusted code. But what typically happens is you need to provide this execution environment for honest users. And there are several different strategies to make this secure. For example, the first one I already mentioned, you have user space in operating systems and permissions for file systems that can somehow bound what the person can do. You could have a more heavy-handed approach, like use the hardware and its provides hypervisor to limit what the person can do even more. So instead of having the operating system limit the calls, you have the hardware itself. And usually people find ways to get around this, sometimes easier, sometimes harder, but usually this is some sort of privilege escalation, some sort of side channel that you find, or usually exploring some bug in the person who designed the system. Later, we're going to talk about a different type of attacks, which I'll get into more detail, but it's basically trying to just slow down the computation of the other users, not trying to read their data or compromise their code, just trying to slow down other users. That's going to be the main focus today. But first, let's talk about the security itself, like how to avoid being able to manipulate other people's data. So I'll talk about this in the context of the EVM, which is very well built in that sense. So a simple model of the EVM would be like this. You have a bunch of accounts. Each line here is a different account. The accounts that are for external users, like your wallet, it's like this. It only has a balance. It doesn't have storage or code. And you manipulate it with your private key. And some other accounts have storage and code. These are what are called the smart contracts. This in this box here is the full state of the Ethereum machine, basically. So if you have this, you have everything. You don't need extra data to move on with the blockchain. But when you send a transaction to a smart contract, you start to execute code. So that's where the second part comes into play. So when you make a transaction to a smart contract, it will load its code, set the program counter to 0, so start at the beginning of the code. It creates an empty stack and an empty memory. The machine that the VM runs is a stack machine, so it needs this. But it also has a linear memory. And this important variable for later is the gas available for this execution. You could think of it as some number that reduces every time you execute an instruction in the code. And if it hits 0, you drop the execution. Now, this is a very traditional stack machine, but the main difference happens when one smart contract communicates with another. So this can be done. There are opcodes specifically for this. And when this happens, you basically create another copy of this page here. So that's why I piled 3 of them here. So this is the first contract that was executed. Then it called the second one, and it's waiting for the second one to run, and the second one ran a third one. So you have these different program counters, different gas available, stacks, and so on. And when this program here halts, a piece of its memory gets sent to the previous page and pops up until the last page says, okay, I'm done executing. And this whole execution may have changed the storage of these touched contracts, their balances as well. And then when everything is done, you go back to erasing all the intermediate thing and only storing the state. So this is a very well thought through architecture. Some important things to take in mind. So the EVM, this Ethereum machine, it has no access to features of the host. So it cannot open a file on your host, not access the internet. So most of the security we are talking about here is security for the other smart contracts. Your biggest fear would be for a malicious smart contract to change the storage of legitimate users one. And that's why each contract has its own storage. It's basically a hard disk that is permanent, and only its own code can modify its storage. So I said here that calling this contract could change the storage of the second contract only because this code had ordered so. This code does not have access to this storage. So in this sense, the smart contract that got called, the second one here, can treat the call as an external transaction, just like if an external user had interacted with it. So this is good because it makes the interaction between smart contracts reflect the interaction between external users and smart contracts. This is good to unify the interface and also to increase the interoperability between them. The only problem I see with this design, and it's a problem that has already played itself several times, most notably in the DAO hack, is that this system allows for reentrance. So if you have a contract that calls another contract without knowing it, this second one could call the first one, and now you have 3 pages, and the contract number 1 owns 2 of them, and it can get confused, and problems can arise. There are several ways to mitigate this. For example, you can set a variable that whenever you call someone, you set a variable that doesn't allow you to receive other calls. So this is an expensive but safe method. And there are other methods like call someone else by the end of handling all your internal affairs. But okay, all this is dangerous and has been explored before. Otherwise, it's a pretty safe system. And the problem that I didn't talk about, and that is going to be the main focus today, is resource exhaustion. So imagine that you have one of these smart contracts, the malicious one, not trying to mess with the storage of a legitimate user, but instead just trying to make the system drag to a halt. So this is not very common in traditional virtualization solutions, because there's a very easy solution to this. You just measure time, and if some process, some user is taking too much time, you just halt them or preemptively reschedule them for later. So the problem with this solution, that's the most traditional, most used, for example, everywhere here, this is what's used. So in a smartphone, in a browser, for this game specifically, the scripts, for AWS, if a process is taking too much time according to your clock, you just use the scheduler to halt it. And then you can give it some more time later, but you're not going to be stopping your other users from acting because of this. But this solution is not deterministic, because to be able to say now it's time to stop someone, you should look at the clock. And the clock, of course, is something that varies from one computer to another because of their different speeds, but for several other reasons. So the metering that Ethereum has, and what I'm calling here adversarial metering, is a solution to this very problem. So let's just, before explaining the solution, let's recall what we're trying to solve. Imagine that you have a host that executes codes from both legitimate users and attackers, and the attacker doesn't want to break the security of the system, just want to exhaust the resources. So typical solution would be using the scheduler, but not only it lacks determinism, it has pretty big overhead. If it works well, for example, for AWS, that has one computer maybe being shared by 5 different Docker containers, but it doesn't work so well if you have a ton of tiny little bots that do tiny little things and already pass execution for the scheduler, because this preemptive scheduling requires you to go out of a tight loop in the machine. Okay, so the solution Ethereum came up with is very smart. So you basically, I hinted to it before, you basically give some budget to every contract execution. So when you call a contract, you say, okay, I have 5 million gas to run. And then when it calls another smart contract, it can pass a little bit of that budget to execute the callee. And if the budget runs out, you just halt the execution midair. So this is very interesting. And what it's trying to do is to infer the execution time in a deterministic way, in a way that it will be reproducible between 2 machines. So this sounds very nice. It is nice, but it has several problems. So the biggest problem is that this inference can be done in 2 different scenarios, and these scenarios can differ quite a lot. The 2 scenarios are the maximum time that certain execution can take. So imagine that you infer how much, I give you a piece of code, you execute it, and your own machine, virtual machine, tries to infer how much time it took in a deterministic way. It could be that it undershoot, and what's the maximum amount of time that that the clock actually measured, so clock time that it can take. This is what the attacker will try to do. Build some code that takes much longer than what you infer it to take. So basically, this is what you have to use as the measurement, right? Let's say that someone managed to build a code that with 5 million gas takes 1 hour to run. The maximum amount of time they can make your computer work with 5 million gas. If your block size is 1 million, it's 5 million, you have to make blocks between 1 hour intervals. So you have to use the maximum amount of time, what the attacker basically will do, to set up the conversion between gas and seconds. The problem is, if someone is not trying to attack you, they're not trying to, cause cache misses and things that harm your speed. Basically, the honest users are not. They're actually trying to do the opposite, try to get cache hits to make things faster. Then you go to the average time, and maybe there's a big difference between the maximum and the average time. So imagine that if you're not running the attacker's code, you're running a typical user's code, 5 million gas is processed in 3 minutes. Look at the situation you are right now. You have to put 1 block every hour, because it could be that an attacker is trying to clog your system, but you have to put, you have to put it every hour, but you really feel tempted to put every 3 minutes, because basically you look at the typical usage of your system, and the block is processed in 3 minutes, and then it stays for 57 minutes waiting for the next block to arrive. So when the maximum amount of gas some user can impose on the system is much bigger than what averagely your metering gives, the system underperforms, because you have to overshoot the conversion between gas and time. So this happens a lot, especially if the architecture that you are emulating differs a lot from the architecture that you are using to emulate. So for example, the EVM doesn't have a cache. I showed you how the architecture looks like, right? It has a stack, memory, but it doesn't have a cache. And your processor has a cache that's it's much faster than RAM. Storage for the EVM is usually associated with a hard drive, which is extremely slow. But it could be that your storage is in RAM, because you just used that contract before, or you managed to build an emulator that does this for typical contracts. So all these mismatches, also the fact that you have to calculate Merkle trees for every access to storage, every change in storage, all these mismatches, they make it so that your maximum becomes very far from the average. If you want to make your EVM match better the architecture of the host, you're going to have to make a more complex virtual machine, which is also against the security. Okay, so how do you actually build this measurement system? So the EVM has a gas metering that happens in instruction level. So every instruction, before it executes, it tells you how much gas it's going to take. You look if there is enough gas in the budget to do this, and then it executes the instruction. And it's not only the instruction that you're using, but also some details. So for example, if your instruction is writing 0 to storage, it consumes a certain amount of gas. But if it's writing non-zero to storage, it consumes another amount of gas. So this is the level of granularity that the EVM chose to. And basically the reason it has to go through this very fine-grained metering is because it doesn't trust anyone, cannot. Are there questions or comments? Okay, so let's move on. Here, I'm going to introduce a concept that, okay, I want us to start discussing this. It's something that I think is very different from the Ethereum universe, but I'm no expert in this. I don't think everybody thought about this enough to be an expert yet. So what I'm trying to introduce is this concept of cooperative metering. So let's see what's the biggest difference between, say, Ethereum and Cartesi. Of course, Ethereum is in layer 1. It has to reach consensus from peer-to-peer. And Cartesi can already use layer 1 for several things because it's layer 2. But one of the biggest differences in terms of architecture is that Ethereum hosts applications from many users, among them attackers, while Cartesi is a DApp-specific chain. So the fact that it's a DApp chain basically tells us that there is a single author of code in that machine. Of course, there are examples where there will be several different codes, like the chess game that is being developed. And if someone tries to build the scripts on Cartesi, they're going to run into this. But I would say if that's your use case, you have to develop as an author, you have to develop your own metering. Maybe use Wasmer, which is a very nice VM, which comes with metering already, and it compiles Rust code and so on. But let's not enter into this. Let's think that you're developing an application that will not run code from your end users. So you have a Cartesi machine with a single author. So this is a big difference from the Ethereum situation, because basically you can change your trust or your threat model. So the threat model that I want to introduce is like this. So end users, like someone using your application, they have to trust your developer, or at least read the source code if they don't trust. And the developers have to trust the validators. Of course, there can be many validators, and you can use some consensus algorithm between them. But in the end, if we call hosts the collection of all validators, the developer has to trust the hosts. But this trust doesn't go the other way. So the developers don't trust the users. There could be some user who just trying to send bogus data to your DApp to break it. And the validators don't necessarily need to trust the developer. You know, the validators are going to validate the apps from many people in a preferably unpermissioned way. So there's no reason they would vet all the apps and, you know, trust each one of them. So the trust goes only this way. So what we want to do in the end is to maximize the scalability. So we want to have some system that works for this threat model, but makes the most of the CPU we are using to run the app. So this is a difficult arrow to handle, because the host is the one providing the CPU, and the developer is one coding the app. So how do we handle the fact that the host does not trust the developer? Okay, first things first, in terms of security, there's not a problem, because the Cartesi VM does not execute anything on the host. It does not access the file system in an explicit way. Just like the AVM, the developer cannot break the computer of the host. But it could be that the developer can bring the host execution to a halt, make it very slow. So the solution here is very simple. The host just stops validating that application. So this is a long discussion we already had. So imagine that you are running a hosting system, a validator service, and you start validating the app of a certain developer, and it's taking just too much time. You could just go out of the set of hosts without harming the security of the developers if the other hosts are fine with the time it takes to execute. If, on the other hand, all the hosts are thinking it's taking too much time, or they cannot keep up with the amount of information arriving, then they'll all leave and your DApp is not being validated anymore. That's very risky. So it's up to the developer to make sure that users cannot bring the host to a halt. So you see, the developer is the key here. What it wants to achieve is serve as many good users as possible, valid users, and at the same time, make sure that users acting maliciously cannot send too many things to be processed that halt the CPU of the host. Okay, I think there's too much information here, but I want to keep one simple example in mind to simplify our lives. Imagine that the developer is doing a game, every user is placing moves, but the game, by its own nature, takes a lot of time to process each move, right? So let's say that all the moves take more or less the same amount of time. But if all the users start to send transactions like crazy, your host cannot keep up. Do not follow the amount of data arriving or inputs arriving. So on the other extreme, there could be a DApp that processes so fast the input that there is no possibility for the end users to halt the host, because remember, the users are paying to send the transaction because they have to pay to make their data available in L1. Okay, so basically, this is the setup. I'm going to break this down into smaller pieces, but the setup is in cooperative metering, the host and the developer are not in so much of a distrust relationship. What they are trying to do is together filter inputs from good users and bad users. And here it's very important to emphasize, this is data. This is not code. Oh, sorry. They're receiving data from users, and they're trying to process them and keep things in a reasonable time. So the first thing you could do is to do no metering at all. So the host charges for validation with a monthly fee, say, or maybe a fixed fee for every input or transaction that arrives to that DApp. And this would break if, for example, processing one input takes too much time and some malicious user sends 1,000 inputs per week, and that's just too much for the host to process. So the hope here is that data availability costs in L1 or in the underlying layer will act as a limiting factor. But you see, as soon as your DApp is very computationally intensive, this barrier could not be enough, maybe. Also, remember that data availability cost, which is our savior here, is going to become much cheaper with EIP 1559 and with sharding later. And even more so if we use data availability committee. So if we have a data availability committee, there's basically no limitation to the amount of transactions you can send to the DApp. So if it takes 1 second for your DApp to process one transaction, it would be very easy for an attacker to send 5 transactions per second and your DApp is dead. So the phase 0 works very well before we have data availability committee, EIP 1559, sharding, and your DApp is not crazy computationally intensive. So basically, we have a lot of room to breathe before we implement something more sophisticated than phase 0. The problem comes when one of these things happens. Let's say data availability committee comes, and some computationally intensive DApps start to not keep up. So phase 1 is the simplest one. Let's say you have a fixed amount of gas you charge per transaction. So the transactions arrive to your DApp in the form of inputs, and you have some block size, say 1 million, and you have a notion of epoch, right? And basically every new transaction, you just cut on the block size. And when the block size zeros, you say, okay, you do something to enforce the block size. I'm going to enter into this later, but let's say you just stop processing inputs until the next epoch. When the next epoch arrives, you renew your block size to 100 and start consuming again 1 million per transaction. So this is, although it's phase one and it's very simple, the main complication is already here because of the enforcing of the block size. So let us remember what happens if your block is full on Ethereum. So forget layer 2 for a while. If on Ethereum you have a block that is full, where is this block? It's not mined yet. It's in the hands of a miner who's putting transactions inside that block. So if they put one extra transaction that would cross the boundary of the block size, it would make the whole block invalid. So it would be bad for them as a miner. So they will limit the block size by themselves with no help from anyone else. So the block size on Ethereum is automatically implemented and enforced by the forking rule. On L2, there is a problem because nothing prevents people from sending transactions to L1, right? We are in L2. And if these transactions on L1 are directed to your application, they will keep arriving. Now, of course, you could say, okay, I don't care if they arrive, I'm just going to ignore them. So that's one way to enforce the block size. The problem with this is that the frustration for the user may be big, right? Imagine that you have an application that every day starts with 1 million gas, and after 100 transactions, it stops reading transactions until the next day. So you could do this. You have access to time in the metadata of inputs. So you could implement this. But imagine now you're a user who arrives at noon. So you feel like it's pretty safe because the clock restarted in the morning. But you send a transaction and it has no effect. You spent money and it has no effect. In the case of Ethereum, if your transaction was too big to fit the block, you don't pay anything. But here you pay because you paid for data availability on L1. So one possible solution is to do the front end, be careful enough that it looks, say, okay, if it's less than 7 million gas in the DApp, I'm going to warn you and not let you send the transaction. That's a very reasonable improvised solution. Of course, people may later push and send the transaction anyway because it's close to the minimum, but not so much. Maybe there will be 7 people sending at the same time, and one of them gets reverted. Another possibility would be for the DApp not to process every input, but store it for later execution. This is problematic if storing the inputs takes time. And now you have a buffer, and it can grow quite a bit. So I don't know. This is murky. You could have a buffer just for the next block. That simplifies a bit life. Instead of having an unlimited buffer, you have just 1 million gas buffer. And the most satisfying solution is far from us, is if we have a sequencer that is gathering the transactions from different users and sent to different DApps. This sequencer has the capability of not including the transaction on a layer 1. And this sequencer could say, hey, don't send the transaction right now because the block is full for the DApp you want to interact with. So this would be the perfect scenario. It doesn't have this weird, careful front end, and it never reverts, basically, even if several people send the transaction at the same time. But it's still far from us. Okay, once we have a system that is able at all to enforce the block size, even if it's just the simplified 100 transactions per day, Then we can go to a more sophisticated one. It's actually very simple. It's just instead of charging 1 million gas per transaction, the app reads the parameter of the transactions and tries to estimate how much each transaction costs. So imagine you have a game and someone is sending a transaction, the app looks at the transactions, okay, it's attack goblin. Okay, it knows that this should more or less cost 3 million gas. And then if it's just a drop item, then this should cost 20,000 gas. You know, it can have a simplified way to look at the amount of gas each transaction is taking. It's just an improvement over the fixed 1 million per transaction. Now, of course, it can use the arguments of the function to determine this, just like Ethereum does with opcodes. But the biggest news here is that the granularity is no longer on opcodes, but rather on transactions, which is huge because one transaction may take 5 million opcodes to execute. So all this overhead that Ethereum has to go through when it's running, 1 million opcodes, it has to calculate gas 1 million times. We don't have to pay this. We just calculate the amount of gas upfront when you look at the transaction, and that's it. So of course, to set all these numbers, you have to do some good benchmarking. But you see, the benchmarks here are on our side. Of course, there is the max against average problem. Maybe dropping. Imagine that the app lets you drop any item for the same amount of gas, but there's some item which takes more for the machine to process the dropping of it. Okay, that's a problem with max against average, but it's much easier of a problem because it's data only. You're not running code from users, you're just reading data. Like drop I is data. So I think once we have some system at all to enforce the limitation of the block, maybe just some front end to the some warning on the front end, I think we could go very refined on this later. So what are the steps that I think would be interesting to take a look at? So imagine we do some DApp that uses some outside source of data availability, maybe some data availability committee, maybe some server that acts as a data availability source. We can start to experimenting with DApps that would clog under that scenario because basically there's no limit to how many transactions arrive. And with some simple effort, we could have some enforcement of block size and start developing this. I think this is, as I said, there's still breathing room. We don't have to implement this right now because we are now saved by the costs of data availability on L1. But this will come as soon as committees arrive, or even very computationally intensive DApps, EIP 1559, or, oh, sorry, I'm saying 1559, I'm sorry. All the time I meant 4844, or sharding. And that's it. Thanks a lot. Sorry for the deep dive into technical subject. Are there questions or comments you wanted to make? Newton, please.
Maybe it's a silly question, but I didn't get it. Why it's cooperative metering? What's the cooperative aspect?
So, yeah, although I said explicitly that hosts do not trust the DApp developers. That's true. The relation between the host and the app developer is much less tense than on Ethereum, right? So on Ethereum, the app developer could really be an attacker that could harm the whole system. Imagine you are a miner on Ethereum. You really don't want some attacker to break Ethereum, because maybe you bought some hardware specific for Ethereum, you're very committed to the project, so you want your attackers to be completely isolated from the power of destroying Ethereum itself. Now, on Cartesi, the host and the developer, they have a closer relationship, right? It's not like the host treats the developers with such a big skepticism. They're kind of cooperating a little bit to provide some nice environment for the user. And the developer is the only developer. So there's no code from someone else going into this picture. So that's why I called it cooperative, because the host and the developers are trying to cooperate to provide a good environment for the users. But yeah, maybe it was a bad name. When I coined this name, I haven't thought about the biggest difference yet, which is the fact that you have a sole developer putting code in your chain, right? This, I think, is maybe you should call it dApp chain metering. That's probably the best name, actually. Okay, maybe I'll stop recording